So thank you very much for the kind introduction, and to all of those of you in the audience. I just noticed in the chat window there seem to be people at 4 o'clock in the morning at Noisebridge in San Francisco. So a special welcome for you for getting up quite so early. So the brief I had was to talk about open science, and so I wanted to take this at a quite high level to tease out some of the principles that I feel are important and have helped me to understand how to tackle some of these questions. And so I want to talk in some part about reinventing discovery, and I want to talk particularly about networks. Now, I steal reinventing discovery from Michael Nielsen's book of that name, which I will very strongly recommend for anyone who's interested in this area and looking at getting into it from a starting perspective. It's a really interesting resource. But I want to start from the question of what we mean by open. That's a sort of fundamental question. And is it just about making available things that we already have? Is it just about opening doors to rooms that already exist? Or is it about doing more and changing the way that we actually act? So let's start with actually this word open. What does open mean? And open has a fairly specific meaning in this space in terms of mechanisms of sharing things that we have already created. And I'm thinking here about open access to existing scientific literature, open data to data sets that have already been created, and open source, which is largely the inspiration for this, of software that's being created. And there are definitions for these things. So the open source definition has a really important part where it says the license must not restrict anyone from making use of the program in a specific field of endeavor. The open knowledge definition focuses on this question of not discriminating against any person or group of people. So to be able to use something for any purpose, regardless of who you are. And for me personally, the Budapest Open Access Initiative defines the term open access, defined it for the first time. And again, it focuses on permitting any users to read, download, copy, distribute, essentially to use research articles for any purpose that they could use it for. So the point here is that anyone can use these things for any purpose. And indeed also all of these, the tools behind this, the legal tools, ensure that once you have a copy of something, you have the rights to use it. So someone can't take away your rights to use it after you've got it. But what about being open? That's what the word open means in this context. But what about this process of being open? Is that another important aspect of this? And I think it is. I think it's critical because it's the thought process, the thinking behind the mechanisms we use to create open content that are critical. And the fundamental underlying aspect of being open is to think that my work can be used by someone somewhere, but I don't necessarily know who that is. So if we think of this as a simple equation where the probability that we can help someone is a function of the number of people interested in the things that I'm doing, how difficult it is for them to use it, and the number of people I can reach. So you can see that these things are related to questions of how usable is the work I've created, how easy is it for someone to use, how many people can actually see it, and obviously the number of people out there who could actually use it. So that's me helping other people, but the other critical aspect of this is the flip side of this, is that someone out there can help me, someone that I don't know, someone that I haven't met, someone that I may never meet, can help me in the work that I'm doing. And again, the same kind of equation holds, except this time the question of interest is the proportion of people that create important things for you. This question of friction is how easy do you make it for other people to contribute to you, to your work. And again, this N, this number of people you can reach that you're in contact with, that you can discover work from. This interest part in both of these equations is kind of fixed because we kind of choose what we're interested in doing. And that probably determines the number of people who are interested. If I'm interested in a particular aspect of structural biology, then there are so many people out there that are interested in it. If I'm interested in a very specific area of mathematics, there might be a smaller number of people working in that space. If I'm interested in some question of ecology or conservation or environmental or health concerns, there's probably quite a lot more. So this is not something, once we've chosen what we're working on, that we can necessarily do a great deal about. But what we can do is look at this friction term and ask the question, how can we make it as easy as possible for someone to use my work? How can I make it as easy as possible for someone to contribute to what I'm doing? And how can I make sure that my work reaches the largest number of people possible? And how can I make sure that the places I look for resources, the number of people who can potentially contribute, is as large as possible? And if we do that, then we can make this term get as large as we possibly can. So being open is just acting to reduce the friction to use or to contribute, and to maximize the number of people who you can reach, who can contribute, who may find out about this, or can discover the work you've created. And critically, it's doing these for both outgoing information and for incoming information. Being open is not just about making things available. It's about making it possible for people to contribute and to recognizing that other people may be able to bring things to the work that you're doing. So these are concepts and philosophical concepts and ways of doing things, but why does it matter? And perhaps most importantly, why does it matter now in a way that it didn't matter 15 or 20 years ago? And it matters particularly because the world has changed. And the world has changed specifically because of the internet and the ability to connect people on a scale that we've never been able to do before. So both N, the number of people we can reach, and the number of people who can contact us is larger than it has ever been before. And the friction, the ease of transferring information or of finding and receiving information, is much greater than it has ever been before. So friction is going down very rapidly and N is going up very rapidly. And there's also something else important about networks. And this is a point where I try to see if we can show this video, if possible. So I've done a simulation of what happens when you take a small network and you start to randomly connect the points up. We're going to be able to bring that video in, or should I do it? Okay. So I've done a simulation. So what should be happening now is that your browser is opening and you're seeing a video open up on your screen. So this is a simulation of me just randomly connecting a set of points on a grid over time. And the graph at the bottom is showing the size of the largest single network that's been created. And what you see is that there are step changes. There are sudden changes where networks get connected together, where you can suddenly reach many more people. And actually, as the size of these grids, the size of these networks grows, those transitions become sharper and sharper. So the opportunity is there to be taken for us to be able to reach many more people than we can today if we find ways to reduce that friction and connect to a wide range of people. So back to the presentation itself. The point I want to make is that there's a huge potential here to do things better and do things more effectively. But we're some distance away from being able to do that and exploit it fully at the moment. We have all this new technology, and if we use it effectively, we can do a lot better. And the bottom line, from my perspective, is that those of us, particularly those of us who receive money from government funders or from charity funders, hold a public trust. We are given money to do research, to create a public good. And in that sense, we have a trust. It is entrusted in us by the public. And the bottom line, to be blunt, is that we can do better with that. And that, at some level, for me, is all that matters. Why does it matter particularly for science? Well, it matters particularly for science because we're in a space where science is a necessary part of solving the problems we face today. And I don't want to belabor this point, but we have issues that we need to face in ecology, conservation, health, society, economics, all of which can be informed by good, effective, and efficient and rapid science. And we just need to do better at helping provide the information that helps policymakers to come to informed conclusions about what policy should be. So given a sort of high-level theoretical background now, let's talk about some actual examples. And I want to avoid the kind of flying car, amazing future kind of stuff that we can often get into. I want to give you some concrete examples of things that have worked. I want to start with something that actually doesn't really come from science, but as many of you will know, particularly in the 19th century, there was a strong tradition of playing chess by correspondence. People would write letters to each other describing the next move they wanted to take, and two people could have this game of chess go over time, slowly, and on a one-to-one basis. Of course, with the telegraph, with the internet, with email, and with network-based services, a lot more people can now play these games of chess with each other. They can discover other chess players. And that's interesting, and that's an improvement on what could be done. But I want to talk about one particular example of a particular chess game where Garry Kasparov was challenged by a group of chess players. And this was a large group of chess players. It was about 50 to 60,000 people. And while they didn't win, and in fact Kasparov actually won the match, he described it later, these are a key, as the greatest game in the history of chess. And in particular, what's interesting about this is that the internet enabled, in a particular way that came together in one case, a very large number of people to contribute to solving a problem playing a game of chess in a way that they could actually compete effectively with the person who was then, may still in many ways be, one of the greatest chess players who's ever lived. Another example that I use quite often is that of Tim Gowers and the Polymath Project. Tim Gowers is a mathematician and a blogger, and he's interested in this question of whether mathematics could be done in a more collaborative fashion rather than one person at a time. And he proposed a project where a group of people came together and solved a particular theorem, proved a particular theorem. And this was actually quite a hard problem that he said. It was not one that he thought he'd be able to solve himself, despite being one of the world's greatest living mathematicians. And what actually happened is that the problem was solved remarkably rapidly by around about 150, 200 people, all of whom knew mathematics, all of whom were mathematicians, some of them world-class mathematicians, some of them school teachers. But together, through a network, by reducing the friction for them to contribute to a problem and by increasing the number, they helped to solve this problem at a pace which was actually unprecedented. Tim Gowers just actually goes on to state that actually the problem was solved not in the way that he'd proposed. So a new kind of solution came out for this problem. And he describes it as a qualitatively different experience to doing research, a really different experience in what was possible in terms of the mathematics at the time. Another example many of you will be familiar with is Galaxy Zoo. Again, the problem here was a very large number of galaxies that needed to be classified into shapes and sizes to do the science. And there were far more than any one person, any one expert could classify. There was a lot of friction to other people contributing because these were in a data set that was not necessarily easily accessible. So by creating a web service, a game almost, where people could contribute, they reduced friction to the difficulty in clicking a few buttons in a web browser, which enables anyone to contribute. And by enabling anyone to contribute, you end up with several 100,000 people actually helping to solve a problem, and in the process changing the face of the kind of science that can be done in this space. A different kind of example, a paper published in PLOS One, middle of last year, 12th September. Now this is a paper that describes a new species of monkey, and this is something that's of interest to a significant number of people, but normally would only have a very small audience. And if you look at, on the right-hand side there, the total article views, and I actually took this snapshot quite some time ago, getting on for 100,000 people had looked at this paper relatively soon after it was created. That's a real step up from the kind of audience a traditional scientific paper would get. So more people, greater N, and less friction because this isn't behind a subscription barrier. But what's really interesting about this is not so much just the paper itself, but that less than a day later, someone had created a Wikipedia page for this species that has gone on to get millions of views. Again, many, many more people engaging with this science than would have been the case if it was published in a traditional subscription journal. Many, many more people easily able to discover and find this because it's been taken out of a scientific journal where, let's be honest, a relatively small number of people are going to look, and into a place where everybody looks for information all the time. And finally, one other example, I just see Matt Todd's appeared in the chat window. This doesn't necessarily apply to just work that can be done online or just work that involves data. There are also examples of lab work where people have taken problems in chemistry, problems in other places in science, and by opening the problem up, have discovered new people that can help them. And this has happened in chemistry, this has happened in other places. You don't necessarily need to reach very large numbers of people. If you can reach the right people who have the solution to your problem, then that's a really powerful way to advance and speed up the science. So basically we have this overall solution where we need to get more people involved and we need to lower friction. And if we start with traditional science down in this bottom corner where it's hard for people to engage, it's hard for people to find it, and there are relatively few people looking at it and engaging, then the question is, how can we push things out further into this space? And so the Polymath project perhaps doesn't involve a huge number of people, only perhaps a couple of hundred. But by reducing the friction to having those people work together, it made new kinds of mathematics possible. If we start with the example of the monkey paper, again, of more interest to start with possibly, and maybe more accessible for more people. By shifting it from a subscription journal to an open access journal, we make it easier for people to find, we make it more accessible to more people. But the big difference happens when that gets transferred into Wikipedia, where it's very easy for people to find, and many, many people are looking at it. And Galaxy Zoo is perhaps one of the best examples of taking a problem that had a lot of friction that involved a small number of people and taking a piece of that problem and making it accessible and easy to very large numbers of people. And in the process, changing what was possible. We think about crowdsourcing and involving people in the process of science who are not traditional professional scientists, then that's things up in this top right-hand corner. But that's not the only place where we can make significant advances. As the Polymath shows, and the chemistry example has showed as well, that if you can reach a few more people, if you can reach the right people and get experts to engage in your problem who you wouldn't otherwise have had contact with, then you can also make a very big difference to what you can achieve. And when we think about experts, we don't need to restrict ourselves to just those people who have professional jobs inside research institutions. There are many experts out there that we can reach through open access, through open data, who can provide contributions to things that we might not otherwise be able to find. For instance, the code that I used to generate that network graph, I found by doing a Google search and pulling it down. There's a particular problem that I couldn't solve, but someone else had actually solved it for me. And by cutting and pasting the code, I was able to actually generate those visualizations. The other piece, of course, is that these are not two different things. There are a spectrum of engagement from the very expert to the very large. And the real benefits will come when we have these two spaces cross over, and people who are expert but who would not think to contribute to a research process will be able to do that, will have a mechanism for doing that, and will find it possible. So what do we need to make this happen? What needs to change? Well, again, we need to reduce friction and maximize N. Reduce the problems of having people engage with the content, the resources, the projects, and maximize the number of people who can discover, find, and engage with this kind of work, with the aim of engaging ultimately the whole world where we can. And there are three critical aspects to making that happen. The first of those I've mentioned a couple of times. The first is access. If people don't have access to research resources, then they can't do anything with them, whether they're researchers, interested parties, members of the general public, journalists, it doesn't matter. If you don't have access, you can't do anything. So the first step is clearly open access to research outputs, both articles and ideally data. And also earlier access, opening up access to before our traditional points in time so that more people have more time to look at these things. I think that one's kind of obvious. The second really important thing is actually having the legal rights to do stuff. If we want people to do things with research, if we want open science to engage people who actually do things, they need the legal rights to be able to take those resources and be able to do things. And the bottom line is that means Creative Commons attribution licensing or public domain dedication. And that's not because these are necessarily the perfect legal tools for solving the problem of enabling people to do stuff, but it's because they're already being used by millions of people worldwide. And it is by being interoperable and by being connected with the systems that people are already using that we maximize N and reduce friction. And then the third key point, and this is the one where we probably have the most work to do, is we need to think about technical usability. We need to think about if someone can find this, they can read it, they're allowed to do something with it. Is it technically possible for them to do something with it? And here we've got a lot of work to do. We need better tools to enable new kinds of use. We need better tools to enable the kinds of use we'd like to be able to do today. We want to be able to enable people to take the resources we've created and ask new types of questions. And in particular, by integrating materials together, by asking different kinds of questions, to start asking about the wood and not just the trees. And we need platforms to help other people build other things on top of the resources we're creating, enable other people to build, engage, and work together and collaboratively. Because the bottom line is, if we want to do this effectively, we don't just need tools, we don't just need legal rights, we don't just need access. We need all of these things to have the building of networks to be deeply embedded into them. That building the networks, making the connections is a central part of what we do every day when we do science. So what does open mean? It means at some level accepting we don't know what our research is going to be used for, and accepting that we don't have all the answers ourselves. At the end of the day, no one has the answers. Certainly no one person has all the answers. So we need to exploit the capability of networks, of the infrastructure, of the web. We need to engineer all of what we do so to create the scale, to maximize that N number. We need to engineer for ease of use, to reduce friction, both ingoing and outgoing. We need to engineer to reduce that friction, and we also need to engineer to support serendipity so that we can create spaces where people make connections and discover things that they wouldn't otherwise discover. And that means that your work can go where it needs to do to make the biggest difference. And it means that the things that you don't yet know about, but are the answers to the problems you have, can find you. And the point is that many people together may have the answers between us. So at the end of the day, what is open science? It's actually nothing more than using networks effectively to do what we want to do better. And I'll stop there, and I'm really interested to look forward to the discussion.